right, so here we go. This is for 2.14. We only have 2 lessons left out of Unit 2. My goal when we started this semester, or when we started this class, was to finish Units 1 and 2 by Christmas break. And so just so y'all know, we're almost there. We've almost done it. I want to talk to you about the first picture up here. Do you see all these data points? Okay. Number 1, my question is it exponential or logarithmic? Logarithmic. Okay, cool. It says the average salary for a church pastor across the U.S. increases as the size of the church increases. The graph above shows the average pastor salaries for various church sizes. We can clearly see a pattern in the data, but the models we have used previously are not appropriate for this data. We have found linear regressions. We have found quadratic regression. We did quartic regression. Lots of different polynomial stuff. We've also looked at exponential regression. None of those fit this set of data. This is going to be a logarithmic regression. Good. Okay. It says the growth above displays a large rate of change initially, but as the church size increases, we see the rate of change gradually decreasing. Okay, so listen. It increases, right? The data is increasing, but as it grows, it's increasing at a decreasing rate. So what do you know about this picture? If the rate of change is decreasing, it is concave down. Good. Okay, so the data above appears to be logarithmic. Just as we have seen with other types of functions, many real-world scenarios follow a logarithmic pattern. Outside the salary data in the graph above, logarithmic patterns are found in the way we measure earthquakes. We deal with logarithms when we're measuring sound, acidity. You've probably seen that in chemistry with pH and that kind of thing. Back to pre-cal. This is good. This is fun. In many other contexts, as a result, we need to create logarithmic models for these types of data. Really adverse feelings about chemistry right now, since you don't watch this. For a given set of data, if the input values appear to change proportionately. Okay, so focus, rein it back in. Logarithmic model can be in the form of y equals a plus b natural log x, or y equals a plus b log x. Okay, the only difference is the base. Your calculator tends to go into natural log. When we do this regression on the calculator, it'll come out in that form. Okay. All right, so example 1. It says selected values of the logarithmic function L are given in the table above, where L of x is equal to a plus b natural log x. Use the given data to write 2 different equations that can be used to find the values for a and b. Okay. So we're not going to do on the calculator just yet, because they want us to do this by hand at this point. We want to write 2 equations given this data set right here, where we see x and L of x. Are y'all with me? Okay, so all we have to do first is write the 2 equations. So it says L of x is equal to a plus b natural log x. So for L of x on the top equation, I'm going to have 3 equal to a plus b natural log what? What's the x value when the output's 3? Yeah, natural log 2. So that's our first equation. Our second equation that could be used here is 7 equals a plus b natural log what? 5. Natural log 5. And then it wants us to find the values of a and b. Substitution. You could do substitution. I wouldn't. You could, though. I prefer elimination when I'm dealing with a system. All right. Let's eliminate a variable. Which variable feels like it would be the easiest to eliminate? A. So how might I do that? I'm going to have to multiply the second equation or the first equation, one of them by -1, so that I have opposite signs in A. Are y'all seeing what we're doing here? So I have 3 equals a plus b natural log 2. If I multiply the second equation by -1, I have -7 equals negative a minus b natural log 5. Stack them and add them. Cancel a. B is attached to that natural log. So it's not going to get to cancel, but good thought there. So -4 is going to equal b natural log 2 minus b natural log 5. Oh, yeah. So I did this the first time, and I just kind of followed my gut, and then it worked out. So it's just like you're thinking it's going algebraically. Okay?
So would you stack them, bro?
I'm going to solve for b first. Okay? So how are we going to get b by itself? I've got b natural log 2 minus b natural log 5. Factor that b out. Factor that b out. Okay? So -4 is equal to b, open parentheses, natural log 2 minus natural log 5. What are your properties of logarithms right there? Is there a way we could condense that? 2/5. So -4 is equal to b natural log of 2/5. Y'all following that?
Okay. Oh, okay.
How do we get b by itself?
Divide.
Divide by the natural log of 2/5.
I was going to divide by b, but...
Well, I want b.
Oh, yeah.
So b is going to equal this number, -4 divided by the natural log of 2/5. You're going to put that in your calculator. I'm going to give you a second. Everyone in your calculator. Okay, nobody just sitting around waiting on Nikki. Everybody put it in your calculator. And you're going to get a decimal. And we're going to round that to the nearest 3 decimal places, so the nearest thousandth place on paper. But we're going to store it on our calculator. Okay, the importance of storing is ever increasing.
Can't we just plug in that expression
In a minute.
rounded?
But we don't want it rounded. That's our problem.
Right, so it's not rounded if we just plug that in.
You could, but we could store it for B, and then we could just put the letter B.
Right.
Right. What number did we get? Anybody?
4.36543.
Okay, 4.365. Now, you're going to do Control, CTRL, stow, and I would love if you would store that as the letter B on your calculator. And then put Enter.
Are there actually 4 dimensions?
Y'all with me? Now we need to solve for A.
Plug in B for...
Plug in that letter B into maybe the top one, maybe the bottom one. It doesn't matter. 3 is going to equal A plus B natural log 2. So 3 minus B natural log 2 is A. This is why we want that letter for B, right? We want that number right here. 3 minus B natural log 2. Yeah, swing it to the other side so that we can figure out what A is.
So now would you put B and then parentheses natural log 2?
You could type it just like it looks. 3 minus B. You have to put the times symbol. You have to put B times natural log 2 or your calculator hates its guts. If it
Negative 0.025.
Okay. Negative 0.02. I think it's a 6. What's the letter number after 5?
8.
Okay. 5 and up, bump it up. Truncate if you would like to. You wouldn't be wrong with the 5. Okay. Yeah, whole bunch of fun. But guys, you have to be able to store those values. It could go a little bit further here with this question, and they could ask you to write the model, right? We could write L of x equals that a plus that b natural log x, and we could use that model with a prediction, which is where we're headed. We could do that, but we can only do that with accuracy if we store numbers for a and b. Do y'all see? All right, moving on. So example 2, it says it gives us this whole big long set of data. We've got church size, we've got average salary. I clearly picked the wrong profession. It's fine.
No, you didn't.
No, I didn't. No,
Well, I'm sure you didn't.
not in Pampa. Okay. So example 2 says the table gives the data from the graph at the beginning of the notes related to church size and average salaries for pastors in the United States. Use the regression capabilities of your calculator to find a logarithmic model. So you're going to go into your stat and data and all of this data and spreadsheets, I think is what it's called. Lists and spreadsheets. Okay, so we're going to do that first. Lists and spreadsheets. And you're going to type in your information. And I'll pause on the video while we have a chance at that.
I have negative 91.54 and then 29.9. Okay. Grace has it.
Grace has it? Good. Glad we checked on Grace.
Frankie doesn't have it.
Frankie doesn't have it?
Actually, it's just doesn't have it.
Okay, so if we were writing S of P, did you get it? Okay, so our A number is this negative 91.542. And our B is 29.909. That's accurate to 3 decimals. What you're going to be hinging on is that you can store those values and use them. Okay? And so this is what I learned at lunch. So before we answer question B, I want you to know where to find these values. They are already stored for you. I want you to know where to find them. So do Control Doc. That's going to bring up you a new page. We want to go to calculator. And I want you to pick option var. You see you've variables. Go down to stat A and push enter.
Where are we?
Whoa. Whoa. So later on, if we need that A number, it's right there. And it's already stored for you. The YouTubes, they told me that. If you want the B number, you do var stat B. Game changer. It really is. Because it didn't make it three decimal places. It's the whole A value.
So there's just store it as A and B and
Whoa!
They already populate. They're already there.
All of that information off to the side is zero.
Cool. It's great. Okay, so now let's look at letter B.
and R squared and all that. That's all.
Focus. Letter B. Letter B, it says, using the model found in part A, what is the predicted annual salary? It says using this model, not some estimated version of this model, but this model. That's why we had to put it in F1. Okay, using this model, what is the predicted annual salary in thousands of dollars for a pastor whose church is 500 people? We are looking for the salary for 500 people. So what are we finding?
Why?
We're finding Y when X is 500. So we're looking for S of 500. This is why you had to put it in F1. So you click F1. Or you do var, pick F1, and you're inputting 500.
What?
Inputting 500, and we get 94.329. I went to 5 because I didn't know what to do with the with the 9 and the 5. So the person whose church congregation is 500 people makes $94. $94,000. Good. Okay, so this is the way this question was asked. They said, what is the salary for a pastor of a 500-person church? Right? My question for you is, how many people are in the church of the pastor who makes $300,000?
Oh, you have to set it equal to it.
Okay, so that's the next question. How many people are in the church for the pastor who makes $300,000? So we're saying S of P is equal to 300. Not 300,000. That would be like a lot of people. But we're setting that equal to 300, knowing that it's measured in thousands. Okay? S of P is equal to 300. Okay, so we're going to solve for P. So now, this is the importance of having A and B stored. Okay, so watch this. Watch this. I know this function S of P is in the form A plus B natural log P. Right? And I'm going back to A and B just so that I don't have to keep writing these numbers in all of their glory and all of their decimal places. Let's first solve for P. So how are we going to do that? Not in solve, we can solve. How are we going to do that? What's my first move?
Subtract A.
Subtract A. So 300 minus A is equal to B natural log P. Y'all with me? Now what?
Divide by B.
Divide by B on both sides. So the natural log of P,
So B and natural log are conjoined here.
yes, it's A times, or B times natural log B. Natural log P. Good cow. Divide by B on both sides. So 300 minus A is over B is equal to natural log P. Now, how do I get P?
13.
I got natural log of P is. How do I get P?
E to
All of that over E.
E to the stuff is equal to P. Y'all following that?
4, 8, 4.
Because this is natural log of P.
6, 5, 4.
Hold on, quit yelling. So E to this stuff, 300 minus A over B is equal to P. That's how we get P by itself. We do the, yeah, and you've got A and B. Remember your var stat A, var stat B. That's why we did that. It really is great.
Really is.
Because then you don't have to graph it. And we're accurate. Remember before we weren't great at being accurate because we didn't have the exact decimals, so we had to graph it. But if you'll use the stored values, we're exactly accurate. You get the same number if you graph it.
Did you try it?
Mm-hmm.
Do you spend more time on this class or calculus?
I spend a lot more time on this class right now. Next year I won't. But the first time I teach a class, it takes all of my time. Because I work every problem you work.
Biology.
Well, I work every problem you work. I work every problem physics works. I work every problem algebra 2 works. So you think I'm demanding to you. What'd you get, Maisie? Say it louder.
484,650. That's what I don't have to.
Yeah.
400.
484,
484.
654.
Okay. People. So if he's making $300,000 a year, this is a very large population.
Yeah, it looks like.
Very large population. I don't know how accurate that is. Could be. That means that he's filling up like a huge stadium. This doesn't fill regularly. Okay, so fun fact, I made this problem up, so maybe this works, maybe it doesn't. What I would say, though, is you need to know the difference in when you need to set your function equal to a number and when you need to plug in a number. Okay? Because that's going to happen to you both ways on your homework. Cool? Maybe if I'd have picked a better number instead of like 300,000, maybe if we'd have picked 200,000, we could have gotten closer in that, logarithmic curve. Feels like we let them be really a lot. It's fine. I made my point. Moving on. Example 3.
What's that weird B?
Example 3, that's a beta. That is a Greek letter. It says the most common and preferred method. The most common and preferred method to measure sound intensity level is called the decibel. Decibel. Fun fact. Read the fun fact down here with me. The word decibel comes from two pieces. One, deci refers to the fact that we're in multiples of 10. Bell refers to Alexander Graham Bell, the inventor of the telephone. So that's why we measure in decibels. Anyways, the sound intensity level beta in decibels of a sound having intensity I is modeled by the function this. I actually teach this in physics. It's kind of the loudness factor, the intensity. Okay. I is just X. Beta of I is your Y. Okay. It says the sounds of noisy traffic has intensity of 1 by 10 to the negative fifth power watts per meter squared and corresponds to 70 decibels. A loud concert has intensity of only 1 and corresponds to 120 decibels. So could we use that information to write two equations? Yes, we could. So for an input of 1 times 10 to the negative 5, I converted that earlier. I converted that to 0.0001, and then I wish that I hadn't. Because watch, when we plug into this formula, it's helpful if it's 10 to the negative 5. So watch, corresponds to 70 decibels. So my first equation is going to be 70 decibels is equal to A plus B log of that intensity. And I could go in here with that decimal number, but it's in base 10. So why don't I call it 10 to the negative fifth? What is log base 10 of 10 to the negative 5 power? Negative 5. You see? So I converted to convert. Oh. So if this is in log base 10 and my input is in base 10, it should cancel, right? So this actually is 70 equals A minus 5B. Because log base 10 of 10 to the negative 5 power is negative 5. Are you with me? Okay, so the other one has a sound intensity of 1 and corresponds to 120 decibels. So let's write that one. 120 equals A plus B times log of 1. What is log of 1? No? 0. Because it's answering the question 10 to the what power gives me 1? 10 to the 0 power gives me 1. So this piece actually completely zeroes out. So what do you know? 120 is A. Okay. If they wanted you to write that whole equation, you would probably have 120 equals A plus B log 1. But I think that anybody with a brain is going to say 120 is A. Okay. If they're grading this, they already know that. Okay, so knowing that information, can you solve for B? 70 equals 120 plus B? No, 70 equals 120 minus 5B. I got the wrong equation up here. Minus 5B. So we'd subtract 120 from both sides. Negative 50 equals negative 5B. So B must be 10. So A is 120 and B is 10. Okay, so it says the human eardrum can burst when sounds reach an intensity level of 1 times 10 to the 4th watts per meter squared. According to the model found above, so let's actually write out the model. Beta of I is equal to A, 120, plus B, 10 times log of I. That's our model. According to the model, what is the predicted number of decimals required to burst a human eardrum? So what are we solving for? We're solving for
X. Y.
solving for decibels, solving for Y, when X is when the intensity is what? 1 times 10 to the 4th. So you could go in there and call that 10,000. I would resist the urge to call it 10,000 because it's in base 10 already. So your amount of decibels, we're finding beta of 10 to the 4th. Y'all see what we're doing? We're inputting that 10 to the 4th. Is 120 plus 10 times log of 10 to the 4th, which is what? Log base 10 of 10 to the 4th is 4. So 120 plus 10 times 4, 160. 160 decibels to burst an eardrum based on this model.
Is that true?
Cool beans? I don't know.
It's close. It's close.
160 decibel. All right, audio engineer, what you got? Is it?
Yeah.
Okay, so as you do your homework, understand the importance of storing your numbers. Understand the importance of knowing whether I'm inputting into the function or whether I'm setting the function equal to the number and solving. Okay? You can do both. We did both today. Ready, set, conquer your homework.